So what is a repeated measures ANOVA? A repeated measures analysis of variance, also called ANOVA, is used to determine whether the means of 3 or more continuous variables or measurements at 3 or more time points on the same continuous variable differ for one group. So you're doing one group of participants and you might have 3 time points for them, or you might have 3 variables that are measured before or after different kinds of treatments, for example. This is a parametric test, so for each of your variables, you need to check to make sure it follows our standard bell-shaped curve. And if you're looking for additional help running a repeated measures ANOVA, we've got information on this in the University of Guelph SPSS LibGuide. There's also the layered statistics guide and the SPSS documentation to help you with this. The important thing to remember here is that these are related groups or matched observations. So those are some keywords that are going to come out a few times, but let us begin. What are the assumptions of a repeated measures ANOVA? We have 5. The first is that your dependent variable must be continuous. The second is that your independent variable must be categorical with 3 or more paired groups or conditions. So that's that repeated piece. It has to be repeated across the same participants. The third assumption is that the dependent variable must be approximately normally distributed for each group or condition. So if you had 5 different groups or conditions, all 5 of those must be approximately normally distributed. Our fourth assumption is no significant outliers, and again, that's for each group or condition. And then our fifth assumption, we've got a little star here, meaning we check this when we actually run the test. Our fifth assumption has to do with sphericity, which we'll talk about more on the upcoming slides. Let's go. So our first Our first assumption is that the dependent variable must be continuous. So if we're looking at our fake data set, for example, we can use the first 3 fake data columns. So we're going to look at fake data 1, fake data 2, and fake data 3. If we look in these columns, we can see decimals, we can see ranges of values. This is a giveaway. This is probably continuous data, which means we pass our first assumption. Our second assumption is that we've got a categorical independent variable, and it must contain 3 or more matched groups or conditions. So for example, if I look across the rows, here I can see this participant identifies as male, and they have data for fake data 1, fake data 2, and fake data 3. So within one singular participant, they have data in all 3 of my groups or conditions. So that means this assumption passes because we've got our independent variable. It's got our 3 matched or repeated groups. Our next assumption, we are actually going to check 2 at the same time. This is for normality and outliers. There's a few buttons you have to click to check this. You're going to click Analyze, Descriptive Statistics, and Explore. And when we're talking about repeated measures ANOVA, we check each of the groups or each of the conditions. So if you've got 3 groups, you need to check all 3. If you've got 5 groups, you need to check all 5. So again, to make sure we check this, we click Analyze, Descriptive Statistics, Explore. That will open up the Explore dialog box. And what you're going to do is take your 3 dependent variable columns. And again, they're matched. So you're going to have a column for each group or each condition. You're going to take your 3 dependent variable columns and put it in the dependent list box. You're going to click the Plots button, which will open up the Plots dialog box. And I'm going to get you to uncheck stem and leaf and check histogram. We don't really do stem and leaf, but we want to look at some histograms. We want to look at some plots. And importantly, we want to make sure we check the normality plots with tests button, and then we can click Continue. If you've done all of this for your groups and you're ready to go, you click OK. And this will check normality and outliers in the same output. So what does this actually look like? Reminder, repeated measures ANOVA, each group or each condition you need to check normality. So when you scroll down to the tests of normality table in your output, you should have 1 row for each group or each condition. So here we're checking 3 different groups. We've got fake data 1, fake data 2, and fake data 3, which means we have 3 rows in our output. If you had 50 or more observations, you would be looking kind of in the middle of the table where it says Komglomerov-Smirnov. Here we have fewer than 50 observations per group, so we're going to look on the right-hand side of this table where it says Shapiro-Wilk. And in this table, if your p-value is less than 0.05, this means you have failed the normality assumption. And this is true if even just one of your groups fails. So if any of your groups at all, or all of them, but if any of your groups fail normality, you have failed the normality assumption, and you might not want to be doing the repeated measures ANOVA. You might have to switch to a non-parametric test instead. Here we see we passed normality for one of our groups. So our first group is 0.455, that is greater than 0.05. So this group passes normality, but two of our groups actually fail normality, which is not good. That's how you can check normality using a statistic. We can also check normality using histograms. So we can generate a plot. I made mine red, yours are probably blue. We can generate a plot for each of these different kinds of, for each of our groups. And we're looking at this and squinting a little bit and saying, does it look like our typical bell-shaped curve where it's got the highest data in the middle portion and lowest data on the ends? If we remember, our fake data 1 variable passed normality. And if we look at our fake data 1 variable histogram, we see it kind of makes sense why it passed normality. Most of the data is highest in the middle, and it's a little bit lower towards the end. It's not a perfect example of a bell-shaped curve, but it's not bad, and it passes with the statistics, so we're okay for fake data 1. The trick is if you look at fake data 2 or fake data 3, these don't really look like our typical bell-shaped curve. For fake data 2, we seem to have highest data at the ends, lowest in the middle. And for fake data 3, the left side is really, really high, and then the rest of it almost looks like a standard bell-shaped curve, but our ends, again, are higher than our middle. So fake data 2 and fake data 3 fail by visual inspection and by our statistic. There's one more graph we can look at if we're doing normality checking as well. We can look at our QQ plot. This has a line going across the page with a bunch of data points. My points are red, yours are probably blue. And what we're looking for here is the data point should be falling pretty close to or on that line. If we look for fake data 1, we see it pulls a little bit away here at the bottom, but the rest of the points fall pretty close to or on the line, so that one would pass visual inspection. But for fake data 2, it kind of is like pulling in this S shape, so that's a giveaway that this probably fails normality. And similarly for fake data 3, it kind of makes like this S shape. The data points don't fall very close to that line, so we've probably failed normality for those. So we can use the statistic and visual inspection to assess normality. In the same output, it will also give us information about our outliers. So I've put that on our next slide here. So our next assumption about outliers, there are a few ways to check outliers. Some fields do things like check the mean and standard deviation. You could do that in SPSS. In the Explore dialog box, though, it's really easy to use what's called the box plot method. So it will generate 3 box plots for you in this case, one for each of our 3 groups or conditions. And what your box plot is showing you is it's got its median in the middle, an interquartile range. I made mine red, yours is probably blue, and it's got whiskers. You are looking for any data points that fall outside of those whiskers. So for example, if you had a circle with a number next to it, let's say the number 20, that would mean that row 20 of your data set is considered an outlier. If you had a star with the number 25 next to it, that would mean that row 25 of your data set is an extreme outlier. And we want to be cautious with outliers. It's one of the assumptions of the repeated measures ANOVA. We should not have outliers in our groups. We want to be very careful with outliers when we're doing a test like a repeated measures ANOVA, because outliers can skew your analysis. It can pull your analysis one way or another, especially with a test like an ANOVA, which is using means. If you have an outlier that's really high above everything else, it might be pulling that condition up, and you might end up finding something that you didn't expect to find, or that isn't really a real difference because you left an outlier in. So here we actually have no outliers, so we've passed this assumption, and that's fine. All right. If you have passed all of your assumptions, you can then proceed to conducting the repeated measures ANOVA. This is your warning to always check your assumptions. You don't know if you pass them unless you've actually checked them. Here we've actually failed the normality assumption, so we would not normally do the repeated measures ANOVA. We would normally switch to the Friedman's test. I'm going to show you how to do the repeated measures ANOVA anyway today, just for practice. So how do we do this? We would click Analyze, General Linear Model, Repeated Measures. And this is one of those examples where SPSS hides things a little bit for you. You have to know to look in GLM because a lot of the tests we're doing are GLM tests. And you have to remember it's a repeated design. You've got paired observations. Paired and repeated are common statistical terms that kind of mean the same thing. So you have to click Analyze, General Linear Model, Repeated Measures. If you do that, you will get a repeated measures define factors dialog box before you actually get to the repeated measures dialog box. So this is new for us. We haven't seen this yet in our workshop series. What you have to do here is say the name of your within subject factor. So you can call it whatever you like. Here I've just called mine fake underscore data. So if you were looking at time, for example, you could say time, and then you would put in your number of levels. So if you had 5 different time points, you would say time, 5, and then you would click add. So here we've called ours fake data. We've said we have 3 levels because we're using fake data 1, 2, and 3. And then we click the add button to make sure that it shows up in this little window here saying fake data and then in brackets 3. Then you have to click define. So this is just telling SPSS before you even get to the dialog box you need, how many different factors you have and how many levels of each factor. All right. If you have put that in properly, you will now find the repeated measures dialog box. By telling SPSS on the previous screen that you had 1 factor with 3 levels, it will fill that information in for you in the within subjects variables box. So the within subjects variables box will now have your factor in brackets. So I've called mine fake data. And in this box, it will have 3 slots for you because we've told it there are 3 different variables here, or 3 conditions, or 3 groups. If we had said 5, it would leave you 5 open slots. What you do on this screen is you take your 3, in this case, we're only using 3 groups, and we take it from the left side and we put them in order. If you have an important order, make sure you keep them in order. We put them in order into the within subjects variables box. These should be continuous. You can note that it is continuous because when it is on the left-hand side, it will have a little yellow ruler. If you're using your own data and you don't have a little yellow ruler, it means you're either using the incorrect type of data here, or you've accidentally set the wrong measure in variable view, and you'll have to exit out of this box and go set your measure so that you're using the correct kind of data. So we take our 3 groups and we put them where it says within subject variables. If you then click the plots button, this will open up the repeated measures profile plots dialog box. And what we're going to do here is we're going to take fake data from our factors box and put it where it says horizontal axis. You're just asking SPSS, give me some kind of plot of what's happening. I want a graph. I want to know what's happening with my data set. You have to remember to click this add button down here. This is more important if you've got like a really big graph with a lot of different factors. So for us, it's really easy. We've only got one thing. So it's a bit of a trick to remember to click the add button. And then you can tell it what kind of graph or chart you want. It defaults to line graphs. Bar graphs are normally best for looking at ANOVAs. So generally you'll want a bar graph unless you're doing something very specific with time. Time would sometimes be a line graph instead. Once you've done all that, you can click continue and you're on your way. You also would like to click the EM means button. This stands for estimated marginal means. If you click this box, it will open the repeated measures estimated marginal means dialog box. On the left-hand side here, it has overall in all caps in brackets, and it has fake underscore data. You're going to take your fake data variable and move it to the box that says display means 4. What this is going to do is, if you find a significant ANOVA, you don't know where your differences are, you're asking SPSS to generate your estimated marginal means, i.e. give me some follow-up tests to tell me where my differences are if I have differences. You might also want to say compare main effects and add a confidence interval adjustment. Here I've selected Bonferroni. Bonferroni is pretty common. Might be different in your field. There are different options here, but Bonferroni is pretty standard if you don't know which one to pick. Once you've clicked all of that in the estimated marginal means dialog box, you will click continue. One more button to click. This one's a big one. You're going to click the options button. The options button will open the repeated measures options dialog box. And there's a few things you want to click in here. On the left-hand side, you're going to click where it says descriptive statistics, estimates of effect size, and observed power. Once you've clicked those 3 options, you're going to click continue. And then you've done everything you need to do. You've moved your variables to the within subject variables box, you've made some plot selections, you've asked for estimated marginal means, and you've selected some things in options. When you're ready, you can click OK. If you have done all of that, you will get the repeated measures ANOVA output that looks something like this. Your first table that I want you to look at is called Moshly's test of sphericity. If you remember, our fifth assumption was sphericity with a little star, meaning you check this when you actually run the test. Here we are looking in the sig column. If p is less than 0.05, it means you have failed sphericity and there's something else you need to do. If you have failed sphericity, when you're actually interpreting your ANOVA, you're going to use either the Greenhouse-Geyser line or the Hunt-Felt line. These are corrections that you can apply if you have failed sphericity. Here, our p-value is greater than 0.05. We have not failed sphericity. We're okay. We've passed this assumption. So we're actually going to interpret our ANOVA in the sphericity assumed line, i.e. we're okay on sphericity. We passed. We don't need to worry about applying a correction. So we've passed sphericity. The next table I want you to look at is the test of within subject effects table. They give it a fancy name. This is your ANOVA table. This is where you actually go to read your ANOVA. It's got a lot of information in here. If you were to write this for a paper, you'd probably need your F value. You'd need your degrees of freedom. You would need the significance column. That's your p-value. And you'd probably also want to report partial eta squared as your effect size. So we're going to read the sphericity assumed line for fake data here. We've got sphericity assumed. Our sig value here is less than 0.001. We have found a significant effect. There is something going on. Our groups are different from each other, but we don't know where yet. And I said you're probably going to want partial eta squared. That gives you the size of your effect. Here we're just below 1.0. It's a pretty big effect. There's more in the output to help you make sense of what's going on. So we found an effect, but we don't know what it looks like yet. What do we do now? Well, we scroll down in our output. We've got a graph at the very bottom. We can look at the graph to try to help make sense of what's happening, but we can't use the graph to say where our differences are. We can look at this, but we don't actually know what's happening. There's one other table that tells you where your differences are, and that's your pairwise comparisons table. If your ANOVA is statistically significant with p less than 0.05, you would then scroll and look at the pairwise comparisons. If your ANOVA is non-significant at p is greater than 0.05, you would not look at the pairwise comparisons table. You would stop because your ANOVA is non-significant. So here, the pairwise comparison is telling us, is there a difference between bar 1 and bar 2? So if we look on the left, we can see here's bar 1, here's bar 2. Are they statistically significantly different? 1 versus 2, our sig value or significance value, our p-value, is less than 0.05. We can say that bar 1 and bar 2 are statistically significantly different. What about 1 versus 3? Again, our p-value is less than 0.05, so we can say bar 1 is statistically different than bar 3. Bar 3 is higher than bar 1. And we also want to check bar 2 versus bar 3. Again, our p-value is less than 0.05, so we can say that bar 2 is different than bar 3. On this table, we've asked for a Bonferroni correction. This is for multiple comparisons. Anytime you do multiple tests, you have a chance of making a mistake. We're adding a correction to reduce the chance of us making a mistake. So that's our really quick run through of how to run a repeated measures ANOVA.